Welcome back to Module 9 of an Introduction to Engineering Vibrations, Single Degree of Freedom Systems. And today's learning outcome is to model actual real-world systems using the three system elements we've come up with: masses, springs, and dampers. So we're going to focus on, this is the overall vibrations course. At this point, we're going to focus on taking an actual system, making simplifying characteristics, and coming up with what we call a physical model, which will represent that actual system with masses, springs, and dampers. And we're focusing on this course on single degree of freedom systems. So as a review, we've got our mass at the top, M for linear objects, and I, the mass moment of inertia, for objects undergoing rotational motion. You've got springs, both the linear translational spring and the torsional spring that we developed. And finally, the damper. The damper is proportional to velocity. It dissipates energy in the system, and you can have a linear damper or a torsional damper again. So let's look at an actual system here to start with. This is the undergraduate lab equipment that I showed you earlier. And you can see from this video that there's a spring at the top, a lot of the mass is in the center, and we have a damper at the bottom. So I want to go ahead and model that and make my simplifying assumptions. And so I'm going to start by using lumped characteristics of the spring, damper, and the mass. So I've got this mass. I'm going to say that all of the mass is lumped into that center portion of that lab equipment. So I'm going to say relative to the mass of the spring and the damper, the bulk of the mass is in the center. This is a simplifying assumption. Later in my other courses, we can distribute the masses more, but this is a great first look at how this system is going to vibrate. Above it, we have our spring constant. It's a linear spring with a spring constant K. It's attached to a support at the top. And we're going to say that this spring is linear. And we're going to say that it's a constant parameter. It doesn't change with time. Same with mass. It's a constant parameter. It doesn't change with time. And finally, I have the damper at the bottom with a damping constant C, which is again linear and constant. Doesn't change with time. The only other thing I need for my model is a coordinate, a generalized coordinate, and an unconstrained generalized coordinate that'll show the complete motion of the system. I'll use the coordinate y here. So therefore, I'm also choosing y dot and y double dot as positive downward. And though that coordinate will tell us everything we need to know about the position and the state of the system. It tells us the stretch in the spring, so we can find the spring force. It tells us the acceleration, so we can tell the mass times acceleration of the inertial force of the mass. And it also tells us the velocity, so we can see the force of the damper inside. So that's a good model, a good starting model, a good simple single degree of freedom model for that situation. Let's move on. This is a video again of the grain separator machine, and you can see that it's on a slope. This was an example of where we had desirable vibrations involved in our machine. And so I'm going to lump the characteristics together so that my machine is a single mass. And I've got it on this slope. I'm actually going to restrict it to go along that particular direction so it doesn't move any other direction. So I'm just going to put frictionless surfaces on either side so it just moves down and to the left and up and to the right. I'm going to go ahead and add a linear spring. With a spring constant K. And I'm going to include the damping action. There's some damping there that's going to dissipate some of the energy. So I'll include a damper as well in my model. and it has a damping constant C. The last thing I need is my generalized coordinate. I only need one generalized coordinate for this system. We'll use, let's just use y again. That's the displacement on the slope to get the spring force. And we'll also assume that the velocity is in the same direction to be able to get the damping force. And finally, the acceleration y will be in the same direction to get the inertial force of the mass. And so a very good simple model, lump characteristics, linearity, and constant parameters that don't change with time. Okay, finally another clip. This is the bungee jumper that we saw in the first module. That bungee cord has spring characteristics. It has damping characteristics. So a simple model of that would be the mass of the jumper lumped together, and then springing action. So we've got a spring and damping action. So we've got a damper. All constant parameters, K, C, all linear. The last thing we have to add again is the generalized coordinate y, y dot, and y double dot. And we've taken this real world system in each of these three cases and come up with a nice physical model that we're going to later be able to put into a mathematical model so we can further analyze it. Okay, so this final slide shows each of those pieces of each of those actual systems that I've modeled, the lab equipment shown very nicely rather than my handwriting alone, the grain machine, and the bungee jumper. And we add on, again, the generalized coordinates. I just show y, but y dot and y double dot are in the same direction. So as a summary, this module was to model actual real-world systems, and we used the masses, springs, and damper, which we're going to model the whole world with in our vibrations course. So see you next time.